Hi, AP Chem students. I'm going to go over 17.26 in this video. This is a buffer problem, and we're asked to prepare a pH 4 buffer right there. Now, I'm going to show you how to do this problem both using Henderson-Hasselbalch and rice tables. Some of you will prefer using rice for everything. And some of you, when you get to buffers, you'll decide, oh, I'm going to use Henderson-Hasselbalch for buffers. So just a reminder, Henderson-Hasselbalch equation is only for buffers. You can't use it anywhere else. But rice can be used for any sort of equilibrium problem. So let's take a look here. We have 1.5 liters of a 0.202 molar solution of benzoic acid. So there's our weak acid right there. And we can add in as much sodium benzoate as we need. So this is a solid, and this is the conjugate base of the weak acid. So the first part is just asking for the pH of the benzoic acid solution. Now, one thing that we do need to know before we can get started on solving this problem is we need to know the Ka for benzoic acid. So I'm going to look that up on my table. Now, on an exam, you would be given that to you. You would not have to look that up. So the Ka is 6.3 times 10 to the minus 5 for benzoic acid. All right, so in part A, all they want is the pH of the benzoic acid solution before you add the sodium benzoate, so just the pH of a weak acid solution. So here we're going to write out our acid-base reaction in water, in aqueous solution, and the benzoic acid donates a proton to the water, forms benzoate ion and H3O plus. So here we're going to use our usual rice table. Our initial concentration is given here, 0.02 molar. Don't care about the water. These are 0 to begin with, and we'll do our usual minus x, and plus x. And we end up with these equilibrium values, which we're going to plug into Ka. So our Ka expression, remember, is going to be our C6H5 COO minus over our H3O plus over our benzoic acid concentration. Okay, so plugging this in, we get x squared over 0.02 minus x equals 6.3 times 10 to the minus 5. But these are different by more than 2 orders of magnitude, so we can neglect x. Solving for x, we end up with a concentration of 1.1 times 10 to the minus 3 molar for our hydrogen ion concentration. And then we can take the minus log of this to get the pH. So the pH is going to be 2.95. All right, so that's part A. Now in part B, we want to figure out how many grams of the sodium benzoate we are going to add in to make this buffer. Okay, so we've got this solution. We're now going to add in solid sodium benzoate. We will assume that there's no volume change. Okay, we're going to neglect this volume change that occurs. And so we can keep whatever the milliliters of, well, in this case, liters, 1.5 liters of solution, that volume is going to remain the same. Okay, so how do we do this? We can do this either using rice or Henderson-Hasselbalch. Okay, so first we're going to do this problem from the viewpoint of the rice table. Okay, there are different ways that you can do this. I'm going to just set up the whole table again. Okay, C6H5COOH plus H2O plus H3O plus. Now they tell us that the pH has to be 4 in this buffer. Okay, so there are things that we know in this rice table. So we know the initial concentration here. Okay, we need to figure this out, right? This is our unknown. We're trying to figure out how much of the benzoate we need to add to this solution. This is 0 initially. So here we have our minus x plus x plus x. Okay, and then we get 0.02 minus x here. This is going to be our concentration of benzoate plus x and then plus x. Well, it turns out we know what x is in this case, right? Because we know the pH. So our H3O plus is going to have to be 10 to the minus 4.00, okay, because that's what our pH has to be. So we know this. We know what x is. And since this is much smaller than our initial concentration, we're going to neglect this x and plug this into Ka again. So Ka is going to be our C6H5COO concentration times our x, which is 10 to the minus 4.00, over our 0.0200 molar. And so we can solve for our benzoate concentration. Remember, this is 6.3 times 10 to the minus 5. So our initial benzoate concentration, solving for it, we're going to end up with 0.013 molar. Okay, so there's our concentration. Now, the question, if you look back, though, is asking for how many grams of sodium benzoate. Right now, we only have the concentration of the benzoate ion. So if we figure out how many moles that is, okay, so we have moles of benzoate per liter. And remember, we have 1.5 liters of solution. That will give us the moles. And we know that there's 1 mole of benzoate for every 1 mole of sodium benzoate, so the moles will be the same here. And so then we just need to convert these moles of sodium benzoate to grams of sodium benzoate. So I can multiply this by the molar mass of sodium benzoate, which is 144.11 grams per mole. And solving for this, we get 2.7 grams of sodium benzoate. Okay, so there we go. That's how you would use rice, okay, to solve part B. Now, instead of rice, what if we use Henderson-Hasselbalch? It's a mouthful, so sometimes I just call this the HH equation. So our Henderson-Hasselbalch equation says that pH is equal to pKa plus the log of the base over the acid. Okay, base over acid. So our pKa, remember, is equal to the minus log of our Ka, which is 6.3 times 10 to the minus 5. Okay, and then we have our log of what we're trying to figure out. This is our unknown here. Okay. we know this is 0.02 molar. Our pH needs to be 4.00. Okay, so we can have 4.00 equals the minus log of our Ka plus the log of base, which is our benzoate ion, over our acid concentration right there. All right, so now we need to do some math, okay, and figure out what this is. But if you do the math correctly, you will get the same answer. So let's do the math here. Okay, if we take 6.3 times 10 to the minus 5 and we get the log of this, we end up with 4.00, and we have 4.2, keep a couple extra digits here, 59, plus the log of base over 0.0200. All right, so now let's subtract this from both sides. Okay, so then minus 4.200659. And when I do that, I end up with negative 0.200659. And that equals the log of base over 0.02. Now, in order to get rid of this log, we're going to have to raise 10 to both of these sides. Okay, so this is 10 to the minus 0.2. Okay, I'm going to first do that. And I end up with 0.63 on this side. Over here, when I take my log, raise 10 to the log, I'm just going to end up with base over acid. And then solving for my base here, right, that would be 0.02 times 0.63. And I end up with 0.013, just like before, moles per liter. The rest of the calculation is exactly the same. So you would just take your 0.013 moles per liter, multiply by the volume, then the molar mass to get the grams of sodium benzoate. So it's up to you which technique you use for buffer problems. Henderson-Hasselbalch works just as well as using the Rice table. Okay, so whichever one you prefer, you should master it and stick with it and use that for your buffer problems. Okay, email me if you have any questions. Hopefully this was helpful.